Hey guys, it's been a little while. I just wanted to give you a recap video of momentum and impulse before the Mastering Physics was due on January 6th. We do need to hit the ground running right when we return. So there's no nice little cushy, walk back into the school year. We need to get right into it. The midterm will have momentum on it. It's a decent sized part of it, so we need to do it justice. Hopefully the video just kind of refocuses you and reminds you some things. But if you were sick or something like that beforehand, it also is a good explanation of everything. Any questions, just shoot me an email. All right, so at the heart of it, Newton, when he was worrying about motion, he looked at mass times velocity. That was really the quantity he cared about. His equipment really couldn't measure accelerations very well, so kinematics that we did in the beginning of the year, he really wouldn't have used. He didn't have those fancy motion detectors, you know what I mean? So he would look at collisions and he would look at their masses and their velocity, and he called it something different, but we now call it momentum. And so basically mass is measured in kilograms, velocity is measured in meters per second, so the units for momentum are kilogram meters per second. There's no cute little name that goes with it. That's it. I will point out that this little symbol above velocity tells us that velocity is a vector, right? And so we have that same symbol over momentum, which means direction matters. If something moves to the right, we need to give it a positive value to indicate that it's moving to the right. That'll be helpful when you do calculations, because then if you get a negative answer, you know it's moving to the left, right? Correct? I shouldn't have said right. Anyway, he comes up with the law of conservation of mass. What he did was he studied two things interacting by collisions, and when they collide, he finds, look at this, the total momentum of the whole system is usually conserved. There are some exceptions when there's something outside that forces these collisions or forces the objects in the system from outside. So things like friction, yes, they would be considered be considered an outside force. We also talked about some examples of this. So like an airbag is a perfect example. Your head is going, in a car going 30 miles an hour down a highway or a road, and your car is brought to rest. Whether that's very quickly or very slowly matters a lot to how well you survive that collision. So your head specifically, if it interacts with the steering wheel and collides with the steering wheel, then the amount of time that it takes to stop is going to be very small. Well, that means that the force is going to be very high in order to bring your head to rest. But if we can increase this time, and we can instead flip this and have lots of time, meaning use an airbag, then the force will actually be reduced. And so that's why we use airbags. We want to reduce the amount of force on somebody's head during a collision, and that way it's more survivable. Now, hopefully you can tell that, so conservation of momentum, what it's saying is, and let me just erase this so it's more clear. What conservation of momentum is saying is that final minus initial, right? If I subtract over the initial momentum, then I'll have a change in the momentum. And the change in the momentum for your head is the same regardless. And so if there's no change in momentum, then that means there was no outside force, right? And so that's what most collisions that we're going to study will look like, but not all, right? Most collisions will have momentum conserved. Two carts bump into each other. And when they do, we say that the momentum initial is equal to the momentum final because there's no external force that was interacting with it. We assume that it's frictionless, right? Let's take a look a little bit closer at momentum for this ball. All right, so we throw a tennis ball or something at a wall, right, or shoot it or hit it, and we throw it perfectly horizontally, and the ball has an initial mass and velocity of 2 kilograms and positive 15 meters per second. Positive because it's moving to the right. So the initial momentum then is obviously going to be positive 30 kilogram meters per second. All right, and then we have, here, I'm just going to flip my tablet here, make it easier to write. Then we have the condition of it hits the wall and it bounces back. So the final momentum is, hang on a second here. The final momentum then is still a 2 kilogram ball. We assume it hasn't lost mass, times its negative velocity of 15 meters per second. As a result, it has a negative 30 kilogram meters per second momentum. So was there a change in momentum? Yeah, there was. The wall is essentially what we think of as immovable. Technically, it's connected to the Earth, and if we wanted to look at this whole thing, we could say momentum was conserved there, that the ball hit the wall, which is attached to the Earth, and therefore the Earth must have a momentum that is equal to the change for the ball. But if we want to just look at the ball and assume that the wall is immovable, it cannot move at all, right? Then we look at just the ball as the system. Well, then we say that, yeah, the ball definitely had an initial momentum first. I don't know why this keeps changing on me. The ball had momentum initial plus any force times time is equal to momentum final. And we're just going to look for the change in the momentum. So essentially, we're going to subtract initial from both sides. And when we do that, we see that we have, right, a change in momentum of negative 30 minus positive 30 final minus initial. Of course, the units are still there. And when we do that, we get a negative 60 kilogram meters per second for the change in the ball's momentum. Okay? So if we knew the force or the time that the ball interacted with the wall, we could figure out the other. So, so that's essentially it, right? Negative 60 kilogram meters per second is the change. All right, so let's look at let's look at a collision. All right, so here we have a ball that's moving, a 2 kilogram ball moving at 15 meters per second. That's momentum of object 1. Then we have another collision, another object that's going to collide with. So object 2. In this case, this object can move. It's not a wall. All right, so the momentum for the left ball, or ball 1, initially is positive 30. And I'm going to stick with these numbers just so we're not caught up with the math here. All right, ball 2 has no momentum. It has no velocity. It has no momentum. So the total momentum initial for the system, right, because there's two objects that we're defining as the system in this one. The total momentum is positive 30 kilogram meters per second. Since there's nothing outside like a wall forcing either of these balls, but we're just looking at the balls themselves, then they're the system. And there's nothing external, so we can assume that momentum is going to be conserved. And so we look at the after scenario down here, and we see that ball 1 comes to rest. So ball 1 now has 0 kilogram meters per second, plus ball 2's momentum. Well, guess what? It's like billiard balls. Ball 1 hits ball 2, and ball 2 gains all the momentum from ball 1. And when it leaves with 30, right, 15 times 2, kilogram meters per second, positive 30. And so we end up with a final momentum of positive 30 kilogram meters per second. So was momentum conserved? Was there a change? The change in momentum is final minus initial. 30 minus the 30 gives us a 0 change. Momentum was, in fact, conserved. Okay, that type of collision has a special name. It's called an elastic collision. We'll talk about it in a minute. Let's look at the other kind of collision that we could have here. All right, here we have, right, object 1 has 30 kilogram meters per second. Object 2 has 0. Initially, the whole momentum is positive 30 kilogram meters per second. But here it's going to be a little different. Here we're going to not have bouncy balls. These are not billiard balls. They're going to be balls of clay, right? So you could imagine, like, I don't know, they're floating in space or something. Or you could imagine an air hockey puck, right? But with a little tab of Velcro on it, right? So this air hockey puck has a tab of Velcro around the outside, maybe a ribbon of Velcro all the way around the perimeter, hits another puck with the opposite type of Velcro, right? So if one has hook, the other side has a loop. And so the first object still came in at 15 meters per second. This is the scenario here. This is all the before. Now, what are they going to look like after they stick together, right? Well, they're going to be stuck. And so that doesn't change much, right? We still have to look at momentum 1 and 2. So has the mass of momentum of object 1 changed? No. It's still 2 kilograms. It has a velocity, v, but the other puck also has velocity v. They're really stuck together going the same speed, aren't they? So we really end up with 4 kilograms times some v. And so that needs to be equal to the final momentum. Well, nothing outside occurred, which means we know momentum was conserved, and it's going to be 30 kilogram meters per second. So we can figure out how fast it's going as a result, right? Let's say 30, 4 into 30, right? That's really what we're looking for here, to find out how quickly they're moving. All right. Obviously it's going to be like 7 point something, right? 0.5, I think. All right. And it is a positive number. How do I know it's positive? Well, momentum final was positive, and the direction only comes from the velocity. The mass doesn't have has a direction, right? It's a scalar. All right. So that, I hope, explains literally the only 2 types of main collisions we need to talk about. They're perfect collisions. This one, and the first one, where they bounce off of each other like billiards balls, is called perfectly elastic. They're totally bouncy. They don't stick together at all. The other one, they perfectly stick together. They're perfectly inelastic, right? 2 balls of clay join, and they become one, essentially, one moving object. All right, so let's take a look. What are the qualities of each of these types of collisions? So elastic collisions, perfectly elastic collisions, is momentum conserved? Well, yeah, we just talked about that, right? Momentum is definitely conserved. Actually, maybe a check mark is better, right? Inelastic, was momentum conserved? Yes, it was. So momentum is a great way to look at collisions because it covers both of these 2 types. Now, one thing we will not have in both of them is energy being conserved. In a perfectly elastic collision, energy is conserved. In an inelastic collision, perfectly inelastic, where they stick together, if they started moving and then they stick together like we saw, then energy is actually lost. So we're not going to check this box. Energy is not conserved. Okay? So in the objects sticking together case, you can't use conservation of energy. You can only use conservation of momentum. That's why momentum is so powerful. We can look at both types of collisions. All right, let's take a look. And let me explain. This is a good example for why, to indicate this difference, okay? So let's look at this perfectly inelastic collision and see what happens here, right? Does the object on the left have momentum? Yeah, it has plus 30 kilogram meters per second, mass times velocity. The object 2, the box on the right, they're sliding along a frictionless surface or something, okay? The box on the right